Hello everyone, welcome to another problem session, and today we are continuing solving these problems from Indian 2024 JEE. This advanced physics part 2 or paper 2, and the question is question 5. So this is a question about this electric dipole. I noticed that this JEE 2024 had another dipole problem, this magnetic dipole. Okay, so this is advanced physics paper 2. Okay, so in terms of dipole, there are a couple of things if you know it, you probably would be able to read the problem and immediately see what you need to do. So, so if you have a dipole P, so as a vector, this is a dipole moment. So if you have two charge minus q and plus q separated by a distance d, distances, then you say P equals to QD, just positive unit, and this is a magnitude, and direction is from minus to plus. And if they're really very close to each other, then you can just forget this and you just look at the dipole moment. So you have a P. If you are in an electric field, if this is, so you have a P like over here, and if you have in a magnetic field or electric field is, so some location A, dipole is that way, and angle is theta, then the electric field can be, it may be like that, and maybe like that, but at that point it's that way. So let's look at that way, electric field, and P is that way, the angle is theta. Then you can say what's the force on P by electric field, or torque on P by electric field. So if you know these formulas, then it will help you. So it's going to be del of P dot E. Things might be minus here. See if the P is aligned with the way to see is a minus or plus sign. You can say it's minus Q plus Q. If the electric field is pointed that way, then there's some big positive charge here. This is a positive plate, this is negative plate. You can think of it like that, and then you can actually figure out if you have the sign over there, right? So this is closer to plus, so this is going to be a less energy situation than if this guy was pointed that way, minus Q and plus Q. So this is higher energy and this is lower potential energy. So energy itself will be, let's call it B, will be P dot E, will not capture it. You want a higher energy. So if they're aligned, it's going to be PE, and the anti-aligned in this situation, is going to be minus P. And I want this to be higher energy, so I'm going to have to put a minus. And so if this is the potential energy, then force will be minus del V, and this minus minus cancel out. So this is going to be del of P dot E, right? Let me change my pen here because this pen is really acting up. Okay. Okay, so So from this little bit side, you can actually tell I'm going to have a plus sign here, because this minus will kill this minus, and you have a del of P dot E. So that will be a force on it. And the torque is P cross E. So, so over here, this thing has a shell with a surface charge density sigma. So on this is some charges are placed. Okay, this is surface charge. This is charge per area, and it's uniformly distributed over here. So that's it's going to have an electric field. What kind of electric field will have? Well, outside. So you need to know the electric field of this. So electric field inside is going to be 0 actually. At a point inside is going to be 0. And electric field outside will be like that of total charge placed at the center. So so if I want to figure out the torque of that, I need to figure out this electric field also, because this charge happens to be outside. I mean, this dipole happens to be outside. So this will just be total charge will be so 1/4 pi epsilon naught. Total charge will be 4 pi r square sigma over this r square. R is the distance from the center to at any point, and this will be radially outward. Radially outward if sigma is greater than 0, inward if sigma is less than 0. So electric field, like over here, is going to point it up like that if sigma greater than 0, pointed like that if sigma less than 0. Okay, and they didn't tell you you know, if sigma is positive or negative. Just a very generic thing. So we when you're reading this statement like this, and if you know these things and these things, you'd say, okay, what do we need? We need actually a rotation. So okay, and it says that this this dipole here is kind of like can rotate about this point, and it's got moment inertia is I. Okay, so dipole is free to rotate about the center. So it's kind of like a little needle with some pin in the middle. So this can rotate. All right. You might be wondering how did I get these things, because I needed that for this electric field. How did I get that? Okay, so that to get that, you can use what is called Gauss's law. If you really want to know more about these things, maybe you want to check out my website, physicsbootcamp.org. Okay, so Gauss's law. I can't teach you Gauss law in very short order because it's actually a little bit more involved. But Gauss's law, you can have a Gaussian surface, so I want to know electric field at that point in the inside. So if I draw a Gaussian spherical surface, then flux of electric field through this surface S1, through S1 will be total charge enclosed, that's what's inside, over epsilon naught. And Churchill enclosed is 0 for this point. There's no charge inside. These are all the charges on the surface of the shell. So, and with a spherical symmetry, this integral becomes whatever, say, E at 0.1, E at 0.1 times this distance r in, 4 pi r in square. So this point r in, this is r in, equal to 0. So E at this in point, let's call it in point that's within the spherical shell is 0. Now if you do the same thing for a point that's out here or over here, so it's arbitrary point, so let's call this r out, and you do a spherical shell to get a formula for it. That shell said this is surface S2. So when you do S2, let's call this E out and R out for that point. So E out times 4 pi R out square will be, now it's the entire charge enclosed. So it's sigma times 4 pi R square. That's the whole, this is the area of the shell. And this is the charge density, is this whole thing enclosed over epsilon naught. So you get E out is a 4 pi r square sigma over 4 pi epsilon naught r out square. So r out is what the E depends on. This whole thing is constant. Okay, so that's how you know that. Now with that, I think you should be able to solve this problem completely, okay? Let me pause the video and clean this up, and I can just present the rest of the work. Okay, so we have now a clean slate. So this is the torque formula for this is the dipole, and this is the electric field where the dipole is located, and this is the formula for the electric field from this sigma on it, okay? All right, I added here the unit vector r hat. Sometimes I use u hat r for it, unit vector. This is so you don't cancel these guys out, okay? All right, let's see. You could cancel out 4 pi's from here just to get a simpler formula. The dipole will undergo small oscillation at any value of r. It says at any value of r. So if down here, if I put a dipole here, there's no electric field. There's no electric field according to this. So this is not going to oscillate back and forth. So this definitely is incorrect. That will undergo a small oscillation at any finite value of r greater than r. So it's outside. This is the outside, right? So we're looking at this situation. So let's see if there is a restoring force. So if the dipole is pointed that way, does the torque point that way? Let's see. I'm going to bring it back to a line, and you do right hand rule. So P is pointed this way. Over here the electric field is pointed that way. So P cross R is, so torque is indeed that way. So this is the sense of rotation is that way. Yes. How about if I had the electric field that way, but the P was pointed that way? Will the torque be the other way? And yes, torque is down below. Yeah, so the torque is this is the sense of rotation of torque. So that's true. It's start to bring it that way. It's going to bring it that way. So yes, this is correct. There will be this will go back and forth oscillation, and that is correct. How about the dipole will undergo small system angular frequency? So angular frequency, how do we get angular frequency? We have to write a torque equation of motion. So for distinguishing C and D, so we need to write equation of motion of this dipole. So the direction is, so this is rotation equation motion I'm going to write. So it's going to be some I, and this angle is the angle coordinate d square theta dt square is going to be so if this is the case, then if I point up, look, so it's going to be have to write a vector equation. If you don't write vector equation, the sign will not come out right. But we are expecting the small oscillation. We can bet it's going to turn to minus I times the magnitude of P cross E. It's going to be PE sine theta. Now, if you want to be more algebraic about it and not in conceptual, like I had to put minus sign here by just concept, what we're expecting, you can actually set this equation up as a vector equation, and then you would be fine. I'm not going to do that in a test situation. Probably better to just make sure you're on track of saving time rather than putting lots of other time. Now this doesn't sound like oscillation. For a small angle theta, this will be minus PE theta. So whenever you have this kind of a structure, you have a simple harmonic motion. So when you have like a d square x dt square minus equals to minus omega square x, so this x, you can identify this thing as whatever there is angular frequency. Omega is going to be angular frequency of oscillation. So this comes from simple harmonic motion. So this problem is pretty good because combining a whole lot of things. So omega square is going to turn out to be PE over I. So I have E is going to be E out because I'm outside, so it's going to be this guy. PE will be sigma R square over epsilon naught R square I. So P is P naught. So if omega will be square root of this, omega is positive, and so I don't have to do square root. If you want to do square root, that can save time. But so there are two for C. I have to check for R equals to 2R. So R equals to 2R is going to be P0 sigma R square epsilon naught 4R square I. So R cancels out. So definitely this is not the case. So C is not the case. So C is not the case. How about checking D? R equals to 10R P0 sigma R square or epsilon naught 100 R square I. So this is the case. This is the case. So we'll get a B and D as an answer. Okay. All right. That's it. There was a good problem. There were a lot of parts to it, and I can't kind of summarize it. You really just in summary, you can say that this was a critical thing to know. This was also critical to know, and also this was critical to know. And I would also say this is small angle setup. You know, this how small angle went to that, and this minus sign is crucial. Okay, I'll see you in another video. Bye.